So the idea now for this second lecture, 1 hour or so, is now to describe the X-rays. Remember, very briefly, it showed you where this comes from, where the Bragg's law and all these things are there. But now, how to make what are X-rays? How we can make it? What is the instrument? What is the important thing? Why we need X-rays? Because this, the core is called X-ray crystallography. It means we need X-rays. Why do we need X-rays? That is the first question. Why do we need? Why can't we use microscope? Why can't we do things? And that's the essence for this. So now, in principle or in practice, X-rays are electromagnetic radiation. You already saw this thing, that we have a wave, and wave have a direction, of course, and the wavelength is measured between these two maxima there. And then we have the intensity, the amplitude of this thing. So the higher is this amplitude, the stronger is the radiation. And then it has two major things, the wavelength and the amplitude for this. And you can easily do. But now, you can see here, for a description of a wave, the phase is needed. And this is really the essence. This we cannot know. It's impossible for the technique to do this. Amplitude, we can measure, we can do the frequency, and we can look for the wavelength is known. These two are like known things, but the phase is not. And that was the direct methods development for mathematical treatment is there to help to solve the structure. Without that, it gets very complicated. There are methods to do this, but nowadays, in order to computer programs to do this, that was a big thing in there. But the point in there is that we can consider the electromagnetic radiation, we consider particles called photons, and the photons is associated with energy. The point in there, it is true, that's the case, but in our case, it's easier to try to understand the X-rays based on the wave formulation. And I particularly like this slide because this will tell us why we need X-rays. So X-rays is the wavelength, certain wavelength light, and that's the idea. But now, here we have a length scale in meters. So you can see here, 10 to the power of 3 meters and 10 to the power of minus 12 meters. And now the idea is that what is there for our purposes? So you can consider that here we have objects, real objects. And the idea is that if we take a soccer field, the scale or the wavelength size in order to image a soccer field would be 10 to the power of 2. So with the 10 to the power of 2 radiation wavelength, we would be able to see the soccer field. And then if we go one step down, we go 10 to the power of 1, so we can see a house. And now the idea is that if we want to see a baseball, we should use a wavelength radiation of 10 to the power of minus 1 meters. And now you can see what happened. The smaller is this, so this point when you print it out is 10 to the power of minus 3. So we are actually seeing things in there with a visible light, which means that this is our maximum thing what we can see with the light. With your own eyes, it's very difficult to see a cell. It has to be a big one. But with the microscope, which is using visible light, that's possible. Because we know now that the visible light wavelength is somewhere 10 to the power of minus 6 and minus 7 between there, something like this. So 300 to 800 nanometers, we speak in nanometers. But we like to use the meter scale because it will lead us to very useful definition of length, what we can use in single crystal X-ray diffraction. The point in there is, okay, in order to see a virus, we would need a wavelength to the 10 to the power of 7. Now, with a protein, we would need 10 to the power of minus 8 or 9.5. But now, if we see a molecule, we are now in here in this magic 10 to the 10. And the point in there is now a very nice description for this. 10 to the minus 10 is called Ohmström. And this Armstrong length scale is absolutely perfect because this is the length scale of an atom distances. So in order us to see a molecule, we need to have X-rays. The wavelength of these X-rays is so small that we can separate these entities. And that's why we have to use X-rays. We can't use anything else because if the wavelength is longer, we can't separate the objects. We can't see. And that is the resolution for proteins. So the resolution in a protein X-ray structure is lower. So the wavelength is the same, the resolution is lower because we can't see individual atoms. We can see amino acids, but we want to see individual atoms, and we have to use wavelength which is on this range. And you can see now what are the names for this. So radio waves are here, microwaves, and so on, ultraviolet, and hard X-rays, soft X-rays. We are here on that region. This is what we have to make them, the X-rays. They don't exist naturally, like visible light exists. So we have to make them. And here is how we make the radiation. And we start from there. So we have here a radio waves. So that's the idea. And then we will go to microwave oven. In theory, with the microwave oven, as a joke, you could separate this baseball. But of course you don't do this. But it's just the idea. Okay, then radar, it works here. People are in this scale. And then light bulb is here on the visible. Light bulb like we have here. Now lights, they are all producing now a wavelength of this. And then X-rays, we can have a cyclotron, or here the robot like looking X-ray machine, because it is actually a robot. And the actual, we have to do this. And the point is that X-rays are high energy, highly penetrating electromagnetic radiation and wavelength range. So this is where we are, where we have to be in order to see atoms. And the other, if you consider in here in the lower part, visible light range is from 4,000 to 7,000 angstroms. And we are now speaking about 1 or 2 angstroms. So the visible light is about 4,000 to 7,000 times too long for us to see the atoms. And this is what we have to do. And now, how the X-rays are created. So regardless of the material we have, they are always created in the same way. So what happens here, so we have our atomic nucleus, and the atomic nucleus has electrons in the K, M, and L shell. And what we do, we shoot electrons into the atom. And now when the electron now here comes, it can do several things. So I will put all these things. So events 1, 2, and 3 interact with the vicinity of the nucleus, resulting radiation produce cause, degrees, and momentum, blah, blah, blah. These things are not okay for us. So this creates coherent radiation. So this creates, and so on, low energy, maximum energy, and so on. But the point in there is that the process, our dominant long applied voltage, is insufficient to remove electron from the nucleus. So what we have to do, we have to shoot the nucleus so strongly that the electron jumps. So either you can consider that it jumps to the next shell or it completely goes out. So there will be a hole. And the hole is not permanent, like this in here. So what this wants to do, it wants to return back. It wants to fill up the hole. So we have a hole here in the K shell, then there from the L shell, the electron wants to return back. And when it returns back, it will emit radiation. And this is the X-rays. So when we reach a high enough voltage for this, meaning their speed of the electrons to hit the nucleus, we can see this phenomenon. And now depending on if we kick it hard or harder, so we can kick it also from the K to M or K to L. And now when it returns from here L to K or M to K, it will create a different kind of X-rays. And that's the idea. And regardless of the element where we are using, so we are using a certain, typically it's a tungsten electrode, a cathode, where we take the electrons and we speed them up with a high electric field to hit the target anode, which is this thing. And inside this anode we hit the we just kick the electron out and wait that it will return back and emit the X-ray. And there is an important point here. So if the voltage, so the speed of the electrons is not high enough, there is no X-rays. So we need to do this because the idea we need that thing to happen. And that is the idea of what happens in here. The characteristic radiation emission, where the incident electron, the energy greater than the K-shell bond, collides with it and ejects. And now the electron shall transfer this. It emits them. This is now the characteristic discrete energy packet which released from this. And this now appears to us as mass X-rays. And the point now why, even though the phenomena is always the same, now the target is important. So the point is, what is the type of the element? What is the element we are using to create the X-rays? Will have an impact on what is the wavelength of this radiation created. And we can do this. So it's a very simple thing to do. So the point now is the characteristic peak, which is called the KL and M, and then they correspond to transition, of course. And the transition difference now reflects the energy which is transmitted in the form of X-rays. And the point where the two orbitals involved in adjacent cells, the line is called alpha radiation. And now, if it's separated by another cell, it's called the beta radiation. So this is the idea. These are the two characteristic things. And the point there is that this is, I like this image, hopefully you can see this nicely. So here you can see one spectrum, second, third, fourth, and so on, with the different voltages. So now you can see that this is this kind of a flat spectrum which comes in here now, unless you hit 25. When the voltage reaches 25, these peaks will appear. So these two. So these are the characteristic X-ray radiations which are coming in there. And this is the whole spectrum. And you can see what happens. There are two spikes. Two very strong spikes are coming out of there, which now reflect the energy between the two shells which are there. Either it's alpha or beta. Beta typically is lower in energy. Alpha is slightly higher, but you can see now, depending on which cell it goes, we can have an alpha 1 and alpha 2 for this kind of a thing. But now, this is very difficult to separate, so we consider that this is like a 1 radiation, and this beta is there. The point in there is we cannot use the whole spectrum, because now, remember, if you remember the Bragg's law indicated the wavelength. And the wavelength was one number. So we cannot use a continuous wavelength in there because we would get a blur. So what we have to use is either one of them. So either this K alpha, the wavelength, or this one. So this is nice because we can easily measure them. We know what is the wavelength for this. And now the idea is that if our anode material, so meaning the material where we shoot the electrons and then it releases the X-rays, if that is molybdenum, we get two alpha radiation, K alpha 1, K alpha 2, but we always use the average, weighted average of this, and it's 0.71073 angstroms. This is now very important. This is an angstrom scale, what we are using. And the point in there, this is always what you import when you report when you're using molybdenum radiation. But you can change the anode material and you can take a copper, and now you can see what is the difference. Now the copper radiation, the wavelength is 2 times longer. It has an impact, what is happening. Later on you will see what is the impact of the change of the radiation. And then we can have iron also. The iron is even longer than copper, so we can change. Silver is shorter than molybdenum radiation. So what means that if we are able to treat our instrument and change this anode material, we can change the wavelength. But remember, with one experiment, we use only one wavelength. So we have to do this thing. We have to select, are we using this wavelength, the molybdenum wavelength, or are we using copper, which are the normal ones. So molybdenum and copper are the things we use. We cannot use both of them simultaneously. We can repeat the same experiment with copper radiation and with molybdenum radiation, but the result will be the same. The only thing is there that the interaction of these wavelength radiations with our crystal might be slightly different. So the longer is the wavelength, the more it will be absorbed by the crystal. So the copper radiation is typically more absorbed than moly. So molybdenum radiation is therefore used in inorganic compounds, and organic compounds and proteins are then studied with copper radiation. But in principle, there aren't any fundamental differences. The only difference is that this peak is in a different position. But that's the idea. This is the easier way to do it. So what we do now, we have to, and it will be in the next slide, we have to have our measurement, we have to have our instrument or method to remove this background here and this peak and this here. So we want to keep only this one. And this we'll call monochromatic radiation. Monochromatic means single wavelength. And here we have agreed to use, because these are so close that it's actually not a problem for us. So we can use the average of here. But this we call monochromatic, so we have to use only one. And now we are happy with the Bragg's law, because the Bragg law has now a number, one number only. And that's the idea why we can use this. So that's the idea. And what is the speed we need to get this thing done, so that we can see the characteristics X-rays is between 10 to 100 kV. Typically it's 50. Between 40 to 50 kV is needed. And then we use a power, and you can see the power is much less. When you combine these two, you can get maybe 1,000 watts or so. That's the power we use to create X-rays. But there are different methods, and the question about the synchrotron is that the synchrotron in principle is the same thing, but the speed which is used, I think it's a giga-electron volts or something like that. So it's so huge, the speed of these electrons, that it gives extremely powerful X-rays. But in principle, it's the same thing. But you need to have a certain minimum number for this voltage in order to do this. At the point in the modern powder instruments, they are even done so that you can separate alpha and beta. So alpha 1 and alpha 2, because in powder diffraction it might make a sense. But in single crystal, we can merge them into one diffraction spot, so it doesn't matter for us. There is we don't gain anything by separating these things, so we just use it as this there. And that's just simple mathematics. I will not go too much in there, but this is the description for this, all this, and there is the actual idea for us to understand that we need a certain minimum voltage in order to create the characteristic X-rays, and then we have to have another means to separate the unwanted radiation from those what we need. And this is, again, very simple. It looks, okay, there's a lot of things, mathematics and so on and so on, but actually it's a very simple thing, because we just need a device to do this. And the device, how you make X-rays, is an old invention. It's about 100 years old. And the point in there is that we have different types of how to make X-rays. This is a quite nice cartoon way of doing it. So it's like a glass tube, and inside this glass tube we have a cathode. This is typically tungsten or something like that. When you heat it up, when you heat this up inside the vacuum, you release electrons. And now what you do, you create a voltage between this part and that part. So that means that now the electrons which are removed from this tungsten wire will start to rush into this anode. And now they hit the anode, as we showed previously. They kick out the electron, returns back, and now the X-rays are coming more or less 90-degree angle from the anode. So the X-rays are not coming out from here, it's coming from the side. So this is a technological thing we have to take into account. So our radiation source is always perpendicular to the creation of the X-rays. it's a really nice thing, and it's about, here we have a picture of it. So this is about 25 centimeters times 10 centimeters. Weighs about 3 kilograms, 4 kilograms. In my course, I always show one. I have a one whole tube so everybody can see how it's there. And this is now the cartoon of this. And now you can see that the X-rays are created in this direction, but they come out in sideways. And now they have to come out from this glass tube. So how do we do that? So the one thing, and what is done, is that we have small windows here. So actually, it's difficult to see, but maybe there is a window in here now, a round window. And the round window is made from beryllium metal, because beryllium metal doesn't absorb X-rays. So it's like a window, but you cannot use normal window. So you have to use beryllium for this. It doesn't absorb X-rays at all. But the only difficult thing with beryllium is it's poisonous metal. So you should not touch this beryllium with your hand. But it's okay. But that's the idea. This is the what we call traditional glass X-ray tube. And this is really about roughly the size of this, a little bit bigger than this. And you can buy it from the shop, and the price is something like 5,000 euros, so it would be like 50,000 rupees. Am I correct? 5,000 is, no, it's 500,000. Yeah. 500,000 rupees, or 5,000 euros, so relatively expensive piece of thing. And now the X-rays are coming in there. And then we have also, this is called the stationary anode X-ray tube, and normally the power of here is around 2 kilowatts. And for that reason, you can see the idea that there is a water cooling here. So in this part here, it will melt more or less immediately if you don't cool it down. So you need the water circulation, cooling in here, and it's quite a lot. So 2 kilowatts, so 2,000 watts in a very small compact phase will heat a lot. It will melt if it's not being cooled down. And then the current new systems where you are using this, they are controlling this, and if the water circulation stops, it will shut down the instrument. Because it might then explode the thing. But when there is no power, there is no radiation. So the X-ray tube itself is safe. It only makes X-rays when we have the power on, when we're shooting electrons in there. And now, what we can do, we can change the anode I told you earlier on. So this is the anode, which is creating the X-rays. So typical what we have is a moly, copper, iron, cobalt, chromium, or silver. Other things are also possible. The idea is that then there is a new method called liquid gallium anode, but it's a very special thing. It's like a white horse, but in principle theory is the same. But the point is, it needs a water-cooled to remove excess heat. And that is the idea, and then you can see here the price, roughly 5,000 to 6,000 euros each, and it lasts between 5 to 6 years. So that's the running cost. So the instruments are quite costly to run, in that sense. So this was invented more than 100 years ago. Of course, that's the idea. And the point is that it's still the most used one, because it's a very simple one. And many of their simpler instruments are using this, because it's like a plug and play. You just take it out, put it back, and then you tune it a bit, and that's it. So it's a very handy to use. But the point, of course, you need electronics to create this high power and the potential in there. But in principle, it's a very easy and old invention for this. This is called the old X-ray tube. But then there is another version of this tube, which is in principle it's the same. But now the previous one, we realized that the anode was stationary. The anode was sitting in one point, and the electrons were shoot into it. But now the rotating anode name describes you that now the anode is rotated, so it's like this kind of thing. This is now the anode part of rotating anode. And the point, this is the tube, this is about 30 centimeters or so. In principle, it's a very similar, and there's a very nice cartoon. So you need a rotor, you need to rotate the anode, that's why it's called rotating anode. And now it's not shooting in one particular place, it will shoot a radial area here. And if you look carefully, maybe you can see this is a more lighter area in here. That is where the X-rays have been shot. It goes in here. And this allows much higher power, because this tolerates more power. So this kind of a thing, if we do a rotation, the X-rays are, as earlier, created 90 degrees from the direction of the electrons. The same way, it comes here, out, but it's much more powerful. And this was used previously on a protein crystallography work. These kind of things is what we call the 9 kilowatt rotating anode systems. And the only difference is that the light, the beam is more bright, is more strong. There is nothing more different than that. So that's the reason for this. And then it was considered to be an in-house analog of a synchrotron, because synchrotron is the most powerful thing to be done. But the part in there with the rotating anode, because it's more sophisticated technique, it requires much more things. For example, it requires that this has to be in a high vacuum, and then in order to make a high vacuum inside this kind of a thing, it's not simple and easy. So you need pumps. And then the running costs for this kind of rotating anode are 5 to 10 times higher than with this, what we call the sealed tube, the previous one. And that is one of the reasons these are not that much used. Luckily, this is now changing, and actually our instrument, I already told you, our instrument is using rotating anode, but it's only 1.2 kilowatt, and it's a microfocus, so it's much smaller. So this is also developed a lot. But the actual idea is that it leaves more gear to run it. And then what is now the, let's say, state of the art? This came about 15 years ago, roughly, yes. It's so-called microfocus salts. And in principle, again, it's the same as the traditional tube. It is the same size, roughly the size of this. But how it's done is that now the focus where the electrons are hitting is really small. So because in the conventional X-ray tube is about 1 centimeter, the anode. Here it's microns, tens of microns. So it means that it creates the X-rays to a much smaller area, and then by volume, by the power combined by the small size, you will get much more out of it, so it's more efficient. And what it leads that the point in there is that, where is it? It's not mentioned yet. That they operate about 40 watts. So we still need the high voltage because we need the speed of the electron, but now we don't need to have a huge powers for there, so we can have, it's like a light bulb. And now it looks like this. So the X-ray tube is inside here. This is optics. The X-rays comes from this side. And now, because it's so compact, easy to do, you can have 2 of them in the instrument. So that's what we have in the other instrument. We have copper and molybdenum radiation in the one instrument. And then, by the computer, just you push the button, okay, change the radiation, and it changes the radius. And that's the idea. So this is called the micro source X-ray tubes. They're inside here. And the only difference now is how you create the X-rays, mechanically or technically. And then the point on here is that we need the electronics and so on for this. But this is the current technology, and if you are going to buy a normal diffractometer now, very likely it will have this kind of a micro source available in there, either 1 or 2. These are also rather expensive. This is about $1 million rupees, 10,000 euros. But they last also some like 4 to 5 years maybe at the current stage. So they are a little bit more expensive than the stationary, the classical ones, but they are also 20 times more powerful. So you save energy and time when using these kind of things. And in our university, in our department, we have both. We have this and the rotating anode. system for that. But that is just the technological side of how you do this. And then, of course, finally, the synchrotron radiation, the question how it's done. So if you accelerate the electrons in here, and then you get a huge speed, look here, 10 to the power of 6 electron volts. So that's the idea, that's the speed that is used to do this. And the energies are there, they're high energy electrons, and then they create a high energy X-rays. But in principle, the wavelength, once it's coming out from here, let's say from this one, then it's the same as in-house instrument. But this is the diamond light source here. So it's a facility which needs 100 or 200 persons to run it. So it's easy to understand that no single department or no single university can have this. Australia has 2. UK, I think, has 1 or 2 or so on. Sweden has 1. Germany has a few. France has a couple of 1. And there is this, CNRS is a big facility for this. And the point is now that only one of these stations, they call these stations, only one of these stations could be single crystal X-ray diffraction. You can use many other techniques in here. So when we buy an instrument, it's only making the X-rays, and we can use that, we call it diffractometer. But synchrotron can do many other things also. And only one, typically one beam line is dedicated, so in this kind of a thing. So you can see here now, each of the station here is doing a different thing. And one of them could be dedicated to protein, for example, protein response. But it's extremely difficult technique, very tedious, very expensive. And then you have to, what you have to do inside, in-house, if you have your own instrument, you just grow the crystals and walk to the lab and do the work. In here, you have to either transport the crystals there or go and pick them up and bring it there by yourself. And that's the idea. Sometimes you have to protect them. They are very sensitive to air. You have to keep them in dry ice or liquid nitrogen and blah, blah, blah. Having this in airplane will be really complicated. So the use of synchrotrons is not very useful, let's call it like this. But protein structures are exclusively done by synchrotrons. Now, and the point there is that because we have these many transitions possible, but we want to control that with the power, what we are doing, and the idea is there that now, this is now the, you look here, this is now the radiation, and then we have the 2 spikes there, beta and alpha, right there. And then what we want to do, we want to remove everything else. We need the one radiation only, and this is what we are doing. So now, if you look for this picture, it's the same as in here, but it's only enhanced image. So this is the background radiation, and beta is here and alpha is here. Alpha is now combined, alpha 1 and alpha 2 is combined. So what we have to do, we now trying to do a trick where we remove this one. And now you can see there's this dotted line, this so-called absorption edge. It's another element, a metal typically, which has an absorption, so it absorbs X-ray radiations on this area. And the point is that if we find a metal, typically a metal which has this kind of a thing, by placing this metal in front of the X-rays, it will cut out this part. It becomes this. You can see what happens. So these are in the same scale. So when it's applied, you shoot X-rays through a metal, and the metal has this kind of absorption edge. It will cut down the intensity of the alpha radiation, of course, that absorbs, also alpha. But what happens, it absorbs quantitatively the beta radiation. As you can see now there is virtually no beta radiation. We can use this. This is what we aim. So then this is called monochromatic radiation. And the idea in there is that we call it, in here, which we use metal, we call it a filter. So it's an X-ray filter, and then these are used to create monochromatic radiation. So for example, if you take a zirconium metal, then it will do this. That would be like a molybdenum radiation, K alpha and K beta in molybdenum radiation. If this is zirconium, that will be the product. So in this way we can do this, and it's easy for us to do this. This is a business done 100 years ago. to select this thing. So if we are using, let's say, nickel, we can use cobalt as a filter. If we use copper, we use nickel. If we use molybdenum, we use zirconium. And the point in there is that now these are the anode materials, but we only use two in real life. So we use either copper or molybdenum. So then we can use either nickel or zirconium filter. But that is a very old-fashioned technique. So I used my first of my instruments, what I was using 40 years ago, nearly 35 years ago, was having molybdenum radiation and zirconium filter in there. But it worked fine. So this was what we got out, and I was able to use it in my study. But the point in there is a better way to do this. So we call them beta filters, because they filter the beta radiation out. But the more clever way of doing this is to use a device, again a device. So you notice now that the X-ray diffraction and the instrument so is a device. They're combined, a combination of many devices, because we have to do certain things in there. And the one thing what we are now doing with this is to make it monochromatic, and then the device is called monochromator. And the monochromator can be like this. It could be like curved silicon. So we create here, from the anode, we shoot electrons, we create here, this is the X-rays. And now these X-rays contain both the alpha and the beta radiation. But now the point is, because we have a curved detector, and it will be diffracting from this curved silicon. In a very similar way, it will diffract from our own crystal. But now, because it's curved, it will make, in a sense, that a certain direction of these radiations, alpha is diffracted, but beta is not. So the beta goes through, and only alpha remains. So this is the same trick as with the filter, but this is mechanical, more or less. So it's using diffraction from a curved silicon. And this was the system what we had in the instrument I started to work with in the middle of the 80s. So nearly 40 years. And the idea is that this was the second option to monochromatize this. And then we have monochromatic radiation, it goes to the sample, and now in the sample it diffracts. This is our crystal, it goes to the detector, and we then measure the diffractions with the detector. That comes later. But this is how we can make the X-rays monochromatic. And there is germanium, silicon, graphite, crystals. And they are based on Bragg's law. So we exclude the unwanted wavelength ideas. But then the other one is that you can also do a new technique. You can use mirrors and collimators like this. So here is the X-rays is coming from that side. Now, by moving and changing the spatial orientation of these two things here, they will also diffract now, but they can diffract so that it actually never comes out, the radiation. So it's the same as the monochromator, but now it's like a single tube. And this we call either a mirror or a collimator. The idea is that it collimates the X-rays and removes, it focuses the X-rays and removes the unwanted ones. And that is the idea. And this is how it's now done typically with the new instrument. So this is called the collimators, the new instruments. And then this is the idea. So it comes here with X-ray source. Now it's the capillary that will focus all these things, and we will have a new focused beam which is focused. It's much more brighter because it's been focused. And then the other radiations are out. There is no, it's the one thing which is coming out is pure radiation, what we want. And that is the idea of that. This is the new modern instrument. So like what we have, both new instruments, even this 14-year-old, 13-year-old instrument, is also still has the similar, already has this collimator type of thing. And now there is even additional new features of these. You can even modulate, you can split the beam. We can also do additional modulations on the radiation, on this electronics or the optics for this there. And this is the actual cartoon for these kind of things. And these are all helpful for having a coherent, pure X-ray be? And this is actually what we need. So this is, I will not go through, this is a powder diffractometer geometry, but these are the simplified versions of now the whole diffractometer. So in here, we now create, this is a rotating anode, we create the X-rays, we put them through a monochromator or a filter. Now we do this with the monochromator, they will then hit the crystal. It's monochromatic. This instrument part here is called the goniometer, that's the robot which rotates the crystal. And now when it shoots there, most of these crystals, most of the X-rays goes through on the crystal, but tiny, very tiny fraction will diffract. And this is now what you see in the detector. That's the diffraction image. This is what we need. We don't need anything else from this instrument, but we actually, this is the data what we have. And now this is the different geometry of the same thing. So goniometer, detector, monochromator, and X-ray source. So now, why X-rays? I needed biomolecules. Remember, I already discussed this with you. So the point, what we can see with the optical microscope is the wavelength. The wavelength, the light is moving with this. And this is a cartoon. So you have your eye, a light, a larger object, your eye, you can see an object. But when the objects get smaller and smaller, you cannot anymore, your eyes are not able to focus on it because it's too small. So what you can do is a trick which is now 500 years old, is the microscope. So you use optics to make the image bigger, virtually bigger. It's not increasing in size, but its image is getting bigger. And that's the idea. But the point is that there is a limit for this, because the limit comes from the wavelength of the visible light. And the point is the maximum resolution with the optical microscope is about 400 nanometers. So this is about the 1/2 of the wavelength of the visible light. And 200 nanometers is actually 2,000 angstroms. And remember, our scale is 1 or 2 angstroms, what we are talking about. The light is out of the question, so we can't use microscope. It would be nice to look your molecules and atoms with the microscope, but we cannot. But the point here is an image of a fiber which is being magnified by 500 times. So you can see very tiny objects, but we cannot see anything which is bigger. But that's the maximum theoretical resolution is lambda over 2 on these things. So the point is if lambda is 1, so the wavelength is 1 angstrom, then the maximum resolution is 0.5. And now we can get a better magnification by using electron microscopes. And these electron microscopes, of course, can go from 0.2 to 200 nanometers. 0.2 nanometer is already on the molecular scale. So this is about 2 angstroms. So in here, you start seeing, with the highest possible resolution, start seeing molecules. And the point here are some images. Look, very nice looking animal. It's a tube worm living. So it's fascinating to see this tiny object. We are looking, of course, molecules, but not the living creatures. You would consider this is a horror movie, but no, it's real life. Or then you can have crystals. You can measure, of course, crystal sizes for this. And then you can, this is an AMF tip. You can see that this is actually what it's used. So this is what microscopy can do. So you have sense, stents, and so on and so on. I will not go into these details because this is out of the scope of this. But in principle, the technique is the same, but it's using electrons in many of the cases. And you might have heard about electron diffraction. Electron diffraction is in principle the same as X-ray diffraction. It only uses electrons to do it. And then when you have as STMs and TEMs, you can have a high resolution images, like you can start seeing what I would say a ghost or the image of an atom. You can't really see it, but you can like visualize. Okay, these are atoms, very well organized in there. Or you can do a nanoparticle microscopy, and you can see layers or crystalline structures here. This is also the 2D material scientists speak about crystals, but these are 2D crystals, so they are not really 3D crystals, what we need. So we can image these things, but we can't get diffraction from them because there's on one layer of that. But they call this 2D crystal because it is crystalline structure, but only in 2 dimensions. And here, what you can do with A and M, you can actually nearly see the atoms and bonds like in here. This is a very nice image. And here is the molecular model cartoon showing that, okay, this might come from the hydrogen bond. So you are on the edge of nearly seeing the physical image of a bond. But this is not clear. And here you can see are these pentacene structures. So that's the idea. These are the pentacenes on the surface. And these are images you can see here. Okay, now is this a bond, hydrogen bond, or is it hydrogen or not? It's difficult to say because it's different. But for our purposes, we are looking even deeper. So this is not enough for us. So we have to have a called atomic resolution. We have to see individual atoms. But the idea is now, and you can have these field emission transmission microscopes for that. And then the resolution for the atomic microscope is on a scale of 1 or 2 nanometers. Which is about 10 or 20 angstrom. So that's the idea. We can see this kind of thing. And then we can use X-rays also to do 3D imaging, which is called tomography. And this is the idea. You can see inside an object or the structure of that. That's a material science or technique. And you can, for example, have a block of this kind, and then with this you can image. Or MRI, you can have an image of your brain. And that's information done with the X-ray tomography. And now, to view molecules at atomic level, so the wavelengths what we are using are 0.5 to 2 angstrom. So we have 2 radiations, 0.7 and 1.5. This is what we do. And this is the actual idea of what we are doing. So the point in here is that here we have our crystal. We need an instrument to record the diffraction. So this is the detector. Then we have to transport, we have to modulate, we have to tune the data in a form that the computer can read it. Computer is doing all the calculations. It actually tries to locate the phases from this data. And then there are you. You are the person that do the work with the computer. And then if everything goes well with you and computer, you can create the phases. And when you get the phases, the computer programs can create an electron density map. And this is actually the product. This is what we see. We don't see the molecule, we see the electron density map. So we see this kind of a thing. Look here, the big hills here. This is what we see. And we have to decide ourselves, and this is nitrogen, and this is carbon, and so on and so on. There are some hints and this kind of additional things which will help us. But that's the point. So this part here now, the diffraction image looks like this. And later on in the course we go through, we will see more of the examples of these images. And now there was a question about the reciprocal lattice point. So each of these diffraction spots represents one particular part of the crystal where the diffraction from that space happens. And it reflects itself as a point here in the detector. And we can consider this. And later on you will see where this comes from and why it's needed. Because each individual thing is a single part of the whole information. So the information about how the atoms are organized in this crystal is here inside this diffraction pattern. But each of these individual tiny points contains a tiny fraction of information. So what we have to do here, we are doing the same thing as with the microscope. We take all these things and we focus them. And we collect them. We collect all the information into one. And then later on I will show you as a reference also how it can be, where it comes from. So we call these an image, a diffraction image. And then we collect the images. And then for that we need the instrument to do the movement. Because if we just keep the crystal in one position and shoot X-rays, we get one image. But this one image is not enough for us. So we need to do this. And this is why we need the instrument themselves. And that's the idea. So there's a lot of different steps what we are doing. And what we are doing in this course, we are going a little bit on theory of what happens and why this happens. We look for the crystals, how they look like, we learn how to make them, then we know if we can get this done, we get the data, what can we do with this with the computers, and so on. And finally, visualize the structure, use this computer programs to visualize the structure, because what we are showing is really a model which is placed on top of the electron density. So we are having two things. We have the real electron density from our crystal and then our model. And they have to interlock. They have to be the same. And it's quite often the case that they will say, okay, that how you describe your molecule. So we use chemistry terms to describe the molecule. Okay, what are the atoms? But actually X-rays don't know the atoms. X-rays only know the electron density. So we know how much diffraction power is on that position. And this is something which is very important for us to know. So there are and the X-rays are scattered from the electrons, and the structural image is based on the time average electron density. Because of course the time average means that because the measurement takes either minutes, or hours, or days, but that's the case. And now, theoretical resolution for molybdenum radiation is 0.4 Angstrom. So we can see separate objects which are separated by 0.4 angstroms. There is no atoms which are so close. But it actually means that we can get more information. We can do electron density studies with this resolution. And it's a special technique, the electron density studies. But that's the idea. And there you can see what is the magnification when we are doing for the X-rays, 10 to the power of 8. And that was that. 1 minute past 1. And now, if I understand it correctly, we will have a 1 hour break now, and then we return and change gears. That will be then more soft thing. I am the hard guy, and the softer guys will speak about these things, but I will not be too hard anymore to you, so that's the idea. So we will go like this and have a break for 1 hour. Yes, okay, great, thanks.